afternoon. It's a pleasure to be here. We're just like less than 2 hours away, but I haven't been back here since COVID, so it's great to be back with a sister, brother, whatever, sibling university in Texas. And I guess there's going to be a game next week, which people in College Station are very excited about. So my talk is about the limits of prediction, weather versus climate, and there's nothing wrong with the slide. I made it that way to show that as you look out into the future, things get hazy, and there are limits that we need to be aware of. And so my talk is partly about the book and partly about some research I'm doing and partly like a survey of the field itself. And I'll try to point out which is which as I go along. And I know the audience is fairly general. I'm a head of an atmospheric science department, and I know everybody knows atmospheric science, but this is a very broad department. I'll try to pitch it at the level that most of you can understand what I'm saying. So when people think of science and technology, they think about possibilities. I mean, you can go to the moon, you can predict hurricanes, and we can do it quite well nowadays. Hurricane prediction is really good for a few days. So we think of what we can do, what we can predict, and we keep thinking about what we can do. But science is also about what we cannot do, and that's an important part of science. Einstein said you can't travel faster than light. Heisenberg said you can't predict both momentum and position infinitely with infinite accuracy because there's a constraint connecting them called the uncertainty principle. So the limits in science you want to know about, and if you're going to invest resources in research, you want to know about those limits so you can invest them wisely. So my talk is about limits of prediction, both weather and climate. So since there's a lot of solid earth people in this department, I thought I'll start with the prediction of earthquakes. And this goes back to 1973, and this is from Science magazine, Science Journal. And you can see the headline, Earthquake Predictions, Breakthrough in Theoretical Insight. So in 1973, people were really excited that they could predict earthquakes, okay? This is 1997, same Science Journal. Article says earthquakes cannot be predicted. We're talking about single earthquake. We're not talking about the frequency of earthquakes or things like that. Those are valid research areas. But predicting a particular earthquake is not, people I believe are no longer working on it. I'm not in that field, but that's what is said here. But within a couple of decades, it changed. And here's Italian scientists were sent to jail because they failed to predict it. I thought that's so, 2012, I couldn't believe this, but that's the headline, and that's what happened. And so the question of earthquake prediction has gone through several iterations, and we know the limits. We still study earthquake, we find out which is a more vulnerable region, but we don't try to predict individual earthquakes now. And that's about limits of prediction in solid earth, which is not really my field, but I thought it's a good introduction. The other thing that's often in the news is tipping points. It goes back to this book by Malcolm Gladwell. And tipping point is that normally when you change a parameter, control parameter, the response happens slowly. But sometimes it happens rapidly, and that's called an abrupt climate change or a tipping point. It's like literally tip a cup. You push it slightly, it'll come back. You push it a little more, it'll tip over. So tipping points are very much in the news in discussions of climate change. If you read, it goes well beyond climate science. This is a remark by Janet Yellen, Treasury Secretary in 2022. And if you read the highlighted area, existing fossil fuel infrastructure will be driving us toward reaching climate points this decade. So Janet Yellen seems to think we'll hit climate tipping points in this decade. I don't think so. I'm a climate scientist, I don't think so, but the Treasury Secretary thinks that's going to happen. It's partly because articles in the media which don't exactly cover all the uncertainties in what climate scientists say. There are possible tipping points, it's just that we don't know if it will happen in this decade. Here is from the World Economic Forum, that if you warm below 1.5 degrees Celsius, we'll have cascading climate tipping points. Again, people think we can predict climate so accurately to 1.5 degrees Celsius warming, and we cross it, and then we get into tipping points. It's important because we're going to cross 1.5 in the next 5 years. That's going to happen. And I don't think we're going to fall off a cliff. But there are people who think we can't predict it that accurately. And so the point is, actually $1 trillion decisions are being made based on predictions from the nonlinear dynamical system, and by people who really don't know that much about nonlinear dynamical systems, okay, and their predictability. So that's sort of the motivation. And so weather and climate are complex nonlinear dynamical systems. So is earthquake prediction. And what are the limits on their prediction? So I'm going to focus now mostly on weather and climate, and it turns out they're very different, although they're both nonlinear climate dynamical systems. So this is something which most of you probably know, that there are limits on weather prediction, and this was discovered in the 1960s. Ed Lorenz, a meteorologist at MIT, published a paper with the title Deterministic Non-Periodic Flow. Before this paper was published, people thought that linear systems, nonlinear systems which were exactly predictable. They were either periodic or stationary point. And what Lorenz showed was that you could have a very simple system with three ordinary differential equations that are coupled. It wasn't predictable if you didn't know the initial conditions to infinite accuracy, which is really not possible. So if there's small errors in the initial condition, they grow exponentially, and it affects the final state in unpredictable ways, and that's called the butterfly effect. So Ed Lorenz sort of destroyed the paradigm that nonlinear systems could be indefinitely predicted. So that puts a limit on weather prediction. We'll talk about what actual practical implication of that in a moment. But if you want to see the exponential growth in weather prediction, this is a forecast of Hurricane Harvey. And the cone of uncertainty, actually, it is the error growth that literally represents error growth. And the doubling time scale is like 2 or 3 days. So this is an example of how error grows in weather prediction exponentially. And at some point, this cone becomes so large that it's not very meaningful anymore. So there are limits to weather prediction, and that goes back to chaos theory. And if you look at not just hurricanes, but weather forecasts globally, what's plotted here is the skill of one of the world's best climate weather forecasting models called the European model. On the x-axis is the year, going from 1981 to 2017. And on the y-axis, it's anomaly correlation coefficient. It's a measure of skill. 100% means you can predict the flow exactly at the middle of the troposphere. So typically 60% or above is considered good skill. And the different lines correspond to forecasts at different times. The blue one's a 3-day forecast, and there are two because there's northern hemisphere and southern hemisphere separately. Okay. So the top is the northern hemisphere, and the bottom is the southern hemisphere. And what you can see is that from 1981 to 2020, the skill has increased, but it's plateaued. The southern hemisphere skill has increased more, but it's approached northern hemisphere skill and is plateaued. And next we have a 5-day forecast. Again, the skill has increased and then plateaued. And this is the 7-day forecast, and this is the 10-day forecast. So here there's still possibility for growth in these. They haven't plateaued yet, but these two have plateaued. And that has to do with the Lorenz predictability limit. So it's believed that we cannot predict weather beyond about 2 weeks. You could put $1 trillion in a model, you could get the perfect weather model, but if you don't have perfect initial conditions, you cannot predict weather beyond 2 weeks. And we cannot have perfect initial conditions because we can't observe every molecule in the atmosphere. So theoretically, if you knew every molecule, you could predict it, but it's never going to happen. So the practical limit is 2 weeks. And so people don't invest resources into predicting weather beyond 2 weeks. You can do it better before 2 weeks, but beyond 2 weeks, it really is not possible. So what about climate prediction? So climate prediction actually is fundamentally different from weather prediction. And so this is an example of a climate prediction you might see. This is from the IPCC report. The IPCC is the Intergovernmental Panel on Climate Change that coordinates climate research. And it issues a report every 6 or 7 years, putting out state-of-the-art climate predictions using the most recent models. And this is from 2021. And the x-axis is time, and the y-axis is the warming of the global average temperature. And the predictions start around 2020, 2015, I think, it's around here. So the black line is the observed temperatures, and the spread is sort of the uncertainty in that. And the colored lines are the predictions And you can see it's not just one prediction, there are like 5 predictions. And the reason we don't have a single prediction is because climate depends not just on physical climate system, but also on human activities. To predict climate, we need to know what the boundary conditions of the climate system are. The boundary conditions of the climate system are things like the solar output. We can assume that to be roughly constant over 100 years. But the other is things like the concentration of greenhouse gases, carbon dioxide, methane. And those act like boundary conditions because they affect the solution. And we need to predict them to predict climate. But we can't predict carbon dioxide concentration scientifically alone because it depends on how much fossil fuel we use and how much we emit. So the way we approach it is that we come up with scenarios. We assume that people use lots of fossil fuels or very little fossil fuels. So the SSP 8.5 is considered a high emission scenario, and the blue 1.9 is the low emission scenario. And these are mid-range emissions. So we make assumptions about human behavior because we can't predict human behavior. I mean, we can barely predict the result of an election. So predicting 100 years ahead is basically impossible. So we make plausible assumptions about the bounds of possible human behavior, and then we predict, for each assumption about human behavior, we predict the evolution of global mean temperature. So climate prediction, unlike weather prediction, is a boundary value prediction problem. The actual prediction actually is sort of inherent in the assumption about human behavior, but to translate that to temperature, that's where the scientific models come in. They do a translation from assumptions of human behavior to what that means for temperature. So what are the limits of this kind of prediction? So it's not the butterfly effect anymore. So we can't use the butterfly effect to put limits on climate prediction. Okay. There are other ways to think about it, and that's what I'll get to. So I'm going to get into a bit of philosophy now. My book was actually about the philosophy of climate modeling. There are 2 ways people reason, and one is called inductivism, it's reasoning from experience. It's also called empirical or statistical approach to reasoning. The simplest example of empirical prediction is that, summer follows winter, the sun rises tomorrow. Those are empirical predictions. They're very good. They're based on our experience. Machine learning actually is an example of a massive empirical inductive prediction system. But that's not the only way we reason. And actually, one way I think of inductive learning is evolution itself is inductive learning. If you look at our DNA, it's learned over the years how to do things, how birds migrate. It's inductive learning which is embedded in the DNA of the bird itself. And so humans also think very inductively. We think, oh, this is the worst storm that's happened in my lifetime. That's inductive thinking. And if it's much worse than what you felt in your lifetime, you think climate has changed, which is not actually, it's a sort of fallacious reasoning there. But we often think inductively. The other form of reasoning, which is sort of the basis of a lot of science, is deductive reasoning, is that you talk about things which you never experienced. I mean, astrophysicists talk about supernovas, which you don't really observe except as a dot. And so you build upon simple ideas which you believe to be true, and then you come up with a very complex result. That is called deductive reasoning. And actually an example is that if you use the tilt of the Earth's axis on its orbit to predict the eclipse, you don't predict eclipses inductively. Humans don't live long enough, but you can predict within the minute an eclipse now because you do deductive reasoning of a very simple system. And physical models of weather and climate are also deductive models. We put in laws of physics, which in some ways are inductive, but they're so accurate that we can think of them as being true. And then we build upon that to make weather predictions or climate predictions. And climate models are basically weather models for the atmosphere coupled with models for the ocean, land, and ice. You couple it all together and build a complex deductive model. And so thus far, until maybe 2 years ago, both weather and climate prediction were done with deductive models. That was the state of the art. It is changing as we speak, and I'll talk about that. So before we had these deductive models, physics-based models, weather forecasts were done inductively. A famous one is the forecast in 1944. D-Day was the time when the Allies invaded, occupied Europe, and they needed a forecast for that. And they didn't have computers, they didn't have the modern forecasting infrastructure. And the way they did it was analog forecasts. So the forecaster would have maps of past weather maps. And looking at today's weather map, the forecaster would look back to find the closest analog in the past and use that to make a forecast. And that was the way to make a forecast. And in some ways, that's how machine learning does it. It just does it with a much more sophisticated system. It does a three-dimensional analog forecast. And people had equations of air to make deductive forecasts in 1944, but they didn't have a computer with which to solve it. So that's what changed after that when digital computers were invented. That in 1950, the world's first computer was used to make the world's first deductive weather forecast. They solved a very simplified fluid equation and made a prediction using a deductive approach rather than the inductive analog forecasting. So within 6 years after D-Day, this happened. And this was led by John von Neumann, who was a famous physicist and a mathematician. So he got together a bunch of meteorologists, because he didn't know meteorology, but he knew how to use computers. Got them together. It was in Princeton. They made the first deductive weather forecast. So in terms of philosophical approaches to prediction, we moved from the inductive approach to deductive approach in 1950. And today's models are much more complicated than the model that was used in 1950. The model that ran in 1950, the computer had a memory of 40 bytes. So it took more than 24 hours to make a 24-hour forecast, which was not a real practical forecast. But 40 bytes was the amount of memory it had, and now we have like 40 gigabytes. But today's computers make the kind of forecasts that you see for hurricanes. And so we've come a long way with the deductive approach. And as I said, until about a year or so ago, this was the state of the art for weather prediction. And what has changed now is that AI models are getting really good at weather forecasting. This has happened in the last year, and it's sort of a revolution in weather forecasting that's happening right now. So the pendulum is trying to get back from deductive back to inductive approaches. So here's a graph showing the skill of machine learning climate models. So on the x-axis is time, starts in 2019. And this again is a skill score just like the one I showed earlier. So this is the higher is good. So the red one is a physics-based European model, which is considered the best weather forecasting model. And these are all, everything else is a machine learning model. And in 2019, they were not doing very well. Machine learning wasn't doing very well compared to physics-based models. As you can see, by 2023, they caught up. And 2024, they're actually beating the physics-based models. These models are built by computer scientists who often really don't have much knowledge of physics. It's just pure, they throw all the data in for the last 50 years of weather that we have observed, and out comes this prediction model, and it's beating the traditional, the best physics-based models. So this is sort of a revolution in weather forecasting that's happening. There's still some issues with these models. They have trouble with rain, so it's not a solved problem yet. But I'm pretty confident in about 5-6 years. It takes time for all this to filter to the practical forecasting, that we'll start seeing machine learning-based weather forecast. An important thing is the machine learning model can be 1,000 times faster than a physics-based model. It's very expensive to train. It takes millions of dollars to train these models on the past data. But once it's trained, what's called the inference stage is extremely fast. And I'm sure your phone will be able to do the same forecast for you. So that about 1,000 times faster than the physics-based model. So that's a big change in weather forecasting. It'll still be subject to the limit of 2 weeks. That is separate, but this efficiency is going to increase. So one of the issues that's come up is that because of the success in machine learning for weather forecasting, people say, oh, we can solve climate change with machine learning. There's a lot of talk of that. And there are Silicon Valley billionaires who are pushing AI and data centers, which are using a lot of power and putting more fossil fuels. And they say, oh yeah, we put more fossil fuels, but the data centers will do machine learning and solve climate change. That's not going to work, because first of all, machine learning is an inductive approach, and climate is an unprecedented climate change. It's not going to work. I'll talk a bit more about that. But machine learning is playing a role in weather forecasting, you don't need to understand anything about science to do this. It's sort of a little scary to be a scientist, but that's what it is. So the question I'm going to address somewhat is, can we build pure machine learning based inductive climate models? And we'll talk a bit about that. But so let me talk a bit more about climate models and complexity. So this is the history of the number of lines of code in one particular climate model. It's called the Hadley Center model that's based in the UK over 15 years. So it's going from 1993 to 2008. The top green one is lines of code, and this is the number of files, like different functions. And you can see it started at 100,000 lines in 1993. Now it's approaching 1 million lines of code. And the earliest climate models are going back to 1970s. They were like 1,000 lines of code. And now we are at 1 million lines of code. So models have gone extremely complex. These are the deductive physics-based models. And in addition to lines of code, another way to look at it is what are the processes that are incorporated in these models. So in the mid-1970s, models basically had 3 components: atmosphere, land, and ocean. They're very simple. And these are the different IPCC reports. This is the first assessment, second assessment, third, fourth, and fifth. So this shows for the different IPCC assessments what kind of processes were included in climate models. So then after all this came aerosol. These are small particles in the atmosphere that help form clouds and also reflect sunlight. And then carbon cycle came in, and something called dynamic vegetation, where vegetation responds to rainfall and temperature, and then that affects rainfall and temperature, and you can get this feedback loop. More recently, atmospheric chemistry has come in, things like ozone interactions. And the most recent stuff that's going into climate model is continental ice sheets. So that's, some of you probably work on that. So now they're going to go into climate models. And we're starting to talk about geological timescales here. I mean, thousands to millions of years. But the reason all those lines of code got added is mainly because all these processes got added in climate models. So we saw that as weather models became more powerful, the skill increased over time. And the forecast got better. The short-term forecast got better and saturated, but the long-term forecasts were getting better. So we can evaluate weather models by how well they can forecast weather. It's very easy. It's a very well-defined metric. We can ask the questions, have climate models gotten better? Actually, nobody's been able to answer the question. It's very tricky to answer that question. You'd think it's easy, but it's not. And I'll show you why. This is just to remind you of the weather forecast models. So this is northern hemisphere for the 3-day forecast, the southern hemisphere, and they're saturated. And the reason these two were different initially is that there was hardly any data in the southern hemisphere 40 years ago. But the techniques for using the limited data we have gotten better. That's why those two have converged, and we can make good forecasts in both southern and northern hemisphere. That technique called data assimilation, and that's really improved. So you do have improvement over time. And to look at climate models, as I said, it's difficult to answer the question, have they gotten better? You have to pick a metric, and the answer depends on the metric. So let's pick a common metric that people use. It's called climate sensitivity. Many of you may be familiar with it. If you take the carbon dioxide concentration on the Earth and double it, just suddenly double it. We are, usually it's done with 300 parts per million, which is near pre-industrial. So you go from 300 parts per million to 600 parts per million. How much will global temperature increase? And that delta T is called climate sensitivity. And we can predict climate sensitivity by doing experiments with climate models. We can change the carbon dioxide in a climate model and see how much it warms. And the first such attempt was done in 1979. It was done by 2 people, Suki Manabe at Princeton and Jim Hansen at NASA GIS. Those were the only 2 climate models in the world at that time. They did that experiment, and there was a National Academy report which discussed climate sensitivity the very first time. And they came up with 2 numbers. One was 2 degrees, other was 4 degrees. So they decided that is the range of uncertainty in our knowledge of climate sensitivity. This was 2 models in 1979, and that's the range that you see here. So this axis is climate sensitivity in degrees. So it goes from roughly, they added a 0.5 on each side to make it a range. So they went from 1.5 to 4.5. The actual numbers were 2 and 4. So the National Academy decided this was the range of climate sensitivity in 1979 to guide people to think about climate change. And so every IPCC report redid this calculation, and those are these bars. The bars are from models. And the lines are actually IPCC's own assessment of climate sensitivity. We use some observational data like paleoclimate data. So they don't always agree. But if you just focus on the models, the range has barely budged from these 5 IPCC reports. I'll show you the 6th one in a moment. But unlike the convergence that you see here, you haven't had convergence in this measure of how much is the globe going to warm if we double carbon dioxide. The range is roughly the same. And if you look at the latest, so I added the latest one here, it's actually higher. So the latest IPCC report found the models actually had a broader range than in the past of climate sensitivity. But it came up with a much smaller assessment based on some other Bayesian analysis of paleoclimate data. But the models themselves are not converging to a smaller bout. So by this measure of convergence, the models are not converging, they're perhaps even diverging. But these models are much, much better than the old models. If I take you back, these models have all these processes. The old model didn't have aerosol, they didn't have carbon cycle. They didn't have all of this, but the answer hasn't converged. The models are much better. Nobody would disagree with that in terms of the processes that go in. But in terms of precision or error bars have actually gotten wider. Okay. So improvement in climate models is not intuitive in the sense of improvement in weather models. The skill doesn't go up in any sense that you can define skill. So the way I think about why the spread has increased, even though the models are better, is this way, that there's uncertainty in our knowledge of climate change, like climate sensitivity. You can write it as quantified uncertainty plus unquantified uncertainty. Since climate is such a complex system, you can't quantify all the uncertainties. So you start with a few processes and you quantify the uncertainty. And you keep adding processes, you're quantifying more of the uncertainty and you're reducing the unquantified uncertainty. So as the model gets better, its spread of its forecast for future climate is actually going to increase. Which is weird because if you promise people, oh yeah, I'll build a better model and they give you a very precise forecast of the future, but actually you give a less precise forecast of the future. Because the precision only applies to the quantified processes. And when people did the spread of models in the early days, they didn't consider all the processes. And once you put in all the processes, you're going to find that the spread is actually going to increase. And we still haven't put in land ice sheets, but putting in land ice sheets or interactive carbon could well increase the spread in the forecast. One of the important differences between the current IPCC and the next is that until now, climate models prescribed concentration of carbon dioxide for the scenarios. They're seeing low and high concentrations. For the next iteration, they're not going to prescribe concentration, they're going to prescribe emissions of carbon dioxide. So emissions go into different carbon sinks in land and ocean, and then become concentration, and that's going to add some more uncertainty in the next iteration. So we're getting more realistic, but our forecasts are getting less precise. So the way I think about it is that if you think you can improve the precision of climate forecasts, you don't have a predictability limit, you have what's called a reducibility limit. Increased complexity is going to limit your ability to decrease the error bar. The error bar, as you measure it by the spread of models, you cannot actually decrease it. So what's the benefit of a better climate model? I'll talk about that. It's not in these global average temperature metrics. There is probably no benefit to getting better models for this metric. So coming back to this is the IPCC prediction for 3 different scenarios, and this was a little older AR5, but these are the different scenarios of emissions, and these are the spread among the models for these scenarios. So what you can see by itself is that if you got a better model that somehow reduced the spread by 50%, as I said, that's not happening, but even if it did happen, what you're going to get is this. The error bar will decrease, the scenario error is still the same. The point here is that the biggest uncertainty in our knowledge of the climate in year 2100 is human behavior. It's not scientific uncertainty. Even if you reduce this error bars to zero, this uncertainty is not going to go away. So whether it's worth trying to get the uncertainty down, that's a different question, but it's not like you just keep reducing uncertainty as you go along. It's our behavior that's going to determine the uncertainty. So, so in this talk, what I've tried to do is not predict climate, but try to predict how climate prediction itself will change over time. So in weather models, what we're seeing is that the short-term scale is saturated. The long, that's like 3 to 5 days is saturated. But 7 to 10 days, there's still scope for improvement, and so it's worth investing in that. And hurricane forecasts, they still do a bad job with intensity. They may do better, but whether it's machine learning or physics-based models, we don't know yet. They could both be in play. Climate models, the model spread in things like climate sensitivity may not decrease, the spread may increase. So there's a reducibility limit. You can't just keep reducing the spread. But as models get better with more processes and higher spatial grid, which I'll show those in a moment, you could get better representation of regional things. It may not affect the global temperature, but the regional processes will be better represented. That's a benefit you get. And extremes, like rainfall extremes, will get better. But if you look at global mean temperature, it's not going to get better. I'll talk a bit about how machine learning could improve parts of climate models called prime prediction, but it's not going to improve the whole model because we don't have data from the future to train the climate models for different kinds of climate change. What you can see here is the 3 possible kinds of climate change. And if you look at different scenarios, you could create hundreds of possible types of climate change. If you had data for all of that, you could train a climate model. You don't. So you can't train a complete climate model using machine learning. But you can try to train parts of it and improve. So here are some improvements. This is weather forecasting. The cone of uncertainty from 2003 to 2022. So you can see 2003 was a wide cone. The red one is the narrow one in 2022. The cone has been narrowing over time. For climate models, the grid currently is pretty coarse. And things like clouds are not represented in climate models. They're not resolved in climate models. They're represented using formulas called separate parameter relations or closures, turbulence closures. So this is what the model resolution has looked like since the first assessment report of the IPCC. So it was like a 500 kilometer grid, then it went to 250, 180, 110 grid. We're currently around 100, still around 100, about 87. We're still not switched to 30 kilometer grids because more and more processes are being added. So the cost has gone up and the increased computer power has gone into processes rather than resolution. That's the way it's evolved increasingly. I'll show you some results from some experiments we've done at Texas A&M in collaboration with NCAR. We actually did 25 kilometer global models, and we see some improvements in extreme rainfall, and I'll show you some pictures of that. So this is a project at Texas A&M where we did a quarter degree atmosphere, that's 25 kilometers, to 1 degree, a 0.1 degree ocean, that's 10 kilometers. And that's unusual, and nobody else actually done this large suite of experiments. And we compare this to typical IPCC type of models where it's 1 degree atmosphere and 1 degree ocean. It's 100 kilometer grid. And you can see some of the differences. So here I'm plotting extreme rainfall. And this is the 99 percentile. So look at, throughout the 99% of the rainfall measurement, keep only the highest 1%. And what does its average look like? This is data over here. And this is for 2 seasons, December to February and March to May. I'll also show you the other seasons in a moment. But these are the good seasons for this model. And this is the high resolution, that's the low resolution. And these observations. And what you can see is that the low resolution does a very poor job of capturing the extremes. The 100-kilometer grid is not able to capture the extremes. The high resolution does an amazingly good job capturing the spatial structure of extreme rainfall. It does it well in winter and in spring, high resolution. The low resolution does a terrible job. And this becomes very important for events like Hurricane Helene, that's extreme rainfall. The Valencia event in Spain, that's extreme rainfall. So it's not enough just to predict the mean rainfall, but you also have to predict the extreme rainfall. And so here, going to better models seem to help. But this model is not going to give you a smaller spread in global properties, as I mentioned. If you look, let me show you the other seasons where it doesn't look good. And the high res still looks better than the low res, but it overdoes some of the extremes. Agreement is not as good as it was in the spring and winter. And that's because in spring and winter, rainfall is driven by large-scale systems, which the model is able to resolve at 25 kilometers. In summer, it tends to be more convective, and that the model still has trouble with. And whether we can ever solve that, we don't know until we try even better resolution. But we get incremental benefits in some regions when we go to high resolution. Then I want to switch to AI. What can we do with AI? Can we use it for climate models? And here's a very interesting, it's a preprint which just appeared about a month ago. It's on Archive. It's a group based at University of Chicago. So they did a very interesting experiment. This is a very confusing figure, but I explained what they did. ForecastNet is a machine learning based weather prediction model. It's usually trained on like 50 years of weather data. So what they did was they took ForecastNet, trained it on weather data, and they created another version where they took out all the Category 5 hurricanes, all the Category 5 tropical cyclone, and then retrained it without those extreme hurricanes. And then tried to see if we could predict a Category 5 if it was not in the training data, and it couldn't. So a model trained without Category 5 could not predict Category 5, which is, so it could not predict unprecedented events that are not in its training sample. And they also did something slightly different. They took out Category 5 except in one basin, but kept it in other basins. Like you take out Category 5 in Atlantic, but keep it in the Pacific, and then train it. And then it had some skill in predicting Category 5 in Atlantic, although Atlantic didn't have Category 5 in the training data. So it's able to move some of the skill from one place to another, but if that particular event is not there anywhere on the globe, it's not able to predict that. And that's the whole thing about climate change. We're talking about situations we don't see at all in current data, or it's very infrequent. So if the machine learning model doesn't see those, you'll never be able to predict those. Physics-based models, to the extent they're correct, they can predict unprecedented events because they're deductive models. They're not based on experience. They can do unprecedented simulation. But machine learning will work for weather for the most part, but again, it may not work for the most extreme events that are not in the 50-year training data set. So that's a limitation of your weather forecasting. And for climate, you can't really train the whole climate model using data because you don't have the different possibilities for climate change, the different carbon cycle feedbacks, all that, we don't have that. And so this is the skill on the left. That shows the full forecast net, and this is pressure in the hurricane. ERA 5 is observations, that's the analysis. The blue is the prediction from the model. And hurricane low pressure it means it's a strong hurricane. So the full trained model can predict the low pressure forming. Here they did a random removal of Category 5. And here they did a targeted, they did a random removal of 25% of hurricanes to just check as a baseline. And here they just removed only the Category 5, which amounted to about 25% or so, I think. And the model is no longer able to predict the low pressures associated with the hurricane. They also found even the full model, which predicts the low pressure in the hurricanes, it does not get some physical laws right. There's something called the gradient wind balance. That's a momentum balance against the pressure gradient. And the hurricane simulated by the machine learning model didn't satisfy that physical constraint. Because model just tried to get the basic features right, doesn't get the details right. So it's not very physical, the hurricanes that are simulated, even by the fully trained machine learning models. It sort of gives hope that there's still place for science. And so there's some work I'm doing right now with machine learning. So what we're doing is it's sort of similar to what I showed previously. We're trying to build a machine learning model, but not of the whole system, but just that part of the climate model that makes rain. And currently we have physics-based approximations where you put temperature and humidity in the vertical, and that's used to predict rain. And what we can do is we can take temperature and humidity from observations and take rain from satellite measurements and try to build a column model that predicts rain. And the hope is that because we are localizing it, that will be valid for a broader range of applications than trying to train the whole model. So it's sort of trying to mimic physics to some extent. So as I mentioned, I'll go back to the summary I had before. So machine learning could improve parts of climate models for which you have lots of data. We can use satellite data measurements to improve the processes, individual processes that go into climate models. But it's not, weather models, you can train the whole model with the data, but climate models, it doesn't make sense to do that. So I'll just leave you with the conclusions about the future of prediction. So I just put a picture of the book which discusses some of the ideas about the philosophy of modeling. And also a blog where I haven't written there in more than a year, but I do occasionally write stuff about modeling. So I'll